All right, we are going to talk about parabolas. So parabolas are conic sections. If we intersect two cones like this with a plane at the right angle that it doesn't intersect this top plane or this top cone, but just the bottom cone, what we get is actually a parabola, which is interesting because we have talked about parabolas a lot in terms of like quadratic functions, and we can find their vertex, we can factor them, we can find their roots. But this is going to be a whole new way to think about parabolas. You think you know about them, but just wait. All right, here's all kinds of new words to think about a parabola. So vertex, we know. Axis of symmetry, that sounds familiar, okay? But these are going to be new terms. Here's a focus. There's a focus point for a parabola that's inside the parabola. And there is a line called a directrix on the other side of the parabola, this red line here. And the focus and the directrix are the same distance from the vertex. On either side of the vertex is the focus and the directrix, okay? And then we have this, I find kind of unfortunately named line here called the latus rectum that goes through the focus point, kind of perpendicular to the axis of symmetry, okay? So those are our three new terms. We have a focus, the latus rectum goes through that, and a directrix. And then we also have our vertex and the axis of symmetry, okay? So why do we have these things? Here's how we geometrically define a parabola. The distance from the focus to any point on the parabola is the same as the distance from that point to the directrix. Okay, so this is going to be perpendicular to the directrix here. These two d values are equal to each other. Okay, so that's geometrically what's going on with a parabola, which is interesting. All right, so let's just derive this real quick. Again, like the other ones, this is a little easier. You're not going to have to recreate this, but I think it's important to see where this comes from. All right, so this is the same as the last page. This distance here from the focus point to a point on the parabola is the same as the distance from the parabola to the directrix. All right, so the distance formula for this, from this point to here, for this x to this point 0p. So here we have our parabola with the vertex at the origin, right? Just to make it easy. In a minute, we'll shift it around. But for now, we're just looking at parabolas with vertex at the origin. So x minus 0, right? The x value of this point is 0 squared, plus y minus p squared, right? So as if we made a right triangle here and are using the Pythagorean theorem, using the distance formula. So the square root of those two things added together is just going to be x squared plus y minus p squared. Looks good? All right, so let's actually, so this is going to be equal to y plus p. The distance here is going to be equal to this distance. Well, what is that distance? There's no change in x, right? It's just the distance. This distance is y and this distance is p. So it's just going to be y plus p. Okay, I believe it. Let's square both sides. Okay, we'll square this side, we'll square this side. So the square root sign goes away and we have y plus p squared. All right, so x squared, now we multiply this out, we get y squared minus 2py plus p squared equals y squared plus 2py plus p squared. Yeah? Okay, so what can we subtract? We can subtract a y squared from both sides, and we're a p squared from both sides, and we're left with x squared minus 2py equals 2py, right? We subtract the y squared plus p squared. We got those on both sides. This is what we're left with. And now let's add this to the other side. We get x squared equals 4py. That is the equation of a parabola with a vertex at the origin and a focus p units away. This looks really different, or kind of different, than equations for a parabola that we've seen before. Okay, but this is the one we're going to be working with. X squared equals 4py. All right, if we know p, then we know where the focus point is. We know where the directrix is. We could figure out things about the latus rectum. right? Okay, so x squared equals 4py. All right, so here's x squared equals 4py. If we have a parabola vertex at the origin opening up, what if it's opening down? How are we going to be able to tell that? X squared equals 4py if p is negative. So same equation. This is if p is positive. This is if p is negative. Right? It's going to open down. How about if it's opening to the left or right? It's going to be very similar. We could rederive the equation, but it would turn out to be like, what's the word? Like corresponding, right? Y squared equals 4px. Here, x squared equals 4py. Y squared equals 4px is if it opens to the right or to the left, right? And this is if p is positive. This is if p is negative. Okay, so very similar equations. So here's something that we need to point out. The lattice rectum is, maybe it's easier to look at it on this one. P, this is P. The length of the lattice rectum is 2p. Okay. And this is kind of, I don't know that you need to know this for anything, but it's kind of interesting geometrically. I don't think you're going to need this for any problems. But let's look here. We've got a parabola, vertex at the origin. It's opening to the right. The focus is at 6, 0. So P is 6, right? So notice how long is this lattice rectum? This is 2p. Okay, from the focus to where it intersects the parabola, that length is 2p, right? It's 12, and this is 12 as well. Okay, so the length of this lattice rectum is 4p. The line, if you drew a tangent line just touching at the place that the lattice rectum intersects the parabola, a line that's tangent to that on both sides is going to intersect at the directrix, which is kind of interesting. Like I said, I don't think you need to really know that for anything, so you can just ignore knowing that, but could be interesting. Okay, so now let's do some examples here. Let me shift over to the webcam. All right, here we are. So here's the kind of examples we'll need to do. Graph y squared equals 24x. All right, y squared equals 24x. And we know that the equation we're thinking about here, y squared equals 4px. Right, so right away we can see, okay, our p value is going to be 6, right? All right, they want us to identify and label the focus, directrix, and endpoints of the lattice rectum. All right, so is this going to be opening up or down? We know the vertex for this is going to be at the origin. So here's the vertex. The y squared is the value that is squared. So that tells us it's going to be opening to the left or to the right, right? And p is positive, so we're going to go 6 units in the positive direction. So there's the focus, okay? And so where's the directrix? The directrix is going to be 6 units in the other direction. 1, 2, 3, 4, 5, 6. There's my directrix. So my focus, I can say, is going to be at 6, 0. My directrix is, what's this equation? This is x equals -6. They wanted us to identify and label the focus, the directrix, and the endpoints of the lattice rectum. All right, so if p is 6, so obviously I did not draw this big enough again. I have a tendency to do that. What's our parabola going to look like? It's going to look like this, and our lattice rectum looks like this. What's this point here? Well, the x value is going to be 6, and remember, our p value is 6. It's 2p is this distance here, so -12. And then up here, let's pretend I drew enough. It's going to be 6, 12. Well, so not so bad, right? Once we find P, we know the vertexes. We just go P units in either direction. And this is 2P. Okay? All right, let's find the next example. Graph this one. Graph x squared equals negative 6y. So same thing, identify and label the focus, directrix, and endpoints of the lattice rectum. All right, so x squared equals minus 6y. So x squared equals 4p times y. So 4p equals negative 6. 4p equals negative 6. So p equals negative 3/2, right? If we divide by 4, 6 divided by 4. All right, so x squared equals 4 times negative 3/2 times y. Okay, so we know our p. We know this is going to open up or down because it's the x squared term, or it's the x term that's squared. And it's going to open down because our p is negative 3/2. Okay, so here's our vertex. So we know it's going to open up or down. We're going to go down 3/2 p units. There's our focus. So 0, negative 3/2. Right? And our directrix is going to be in the opposite direction here at y equals 3/2. These are directrix. And where is the end points of the lattice rectum? Well, it's going to be, let's see, this number, negative 3/2 times 2, is going to give us 3. So 3 units either direction. And so we can kind of connect those with a parabola. And let's see, we know this is the x value is 3 and the y value is negative 3/2. And this would be negative 3, negative 3/2. Okay, kind of new way of thinking about parabolas, but not too bad. Let's do another one, example 3. What is the equation for the parabola with focus negative 1/2, 0, and directrix x equals 1/2? Let's find this equation. All right, let's just plot these things because I don't really have any sense of this at this point. Negative, so 1, 2, 3, 1, 2, 3. The focus is at negative 1/2, 0. So there's the focus. And the directrix is at x equals 1/2. So there's the focus and the directrix. So we can tell the vertex is going to be here at the origin. And it's going to open like this, something like that, right? All right, so what form is this going to have? It's going to be the y squared equals 4px, right? Since it's opening left or right. We know our p value. What is our p value? Our p is negative 1/2. So y squared equals 4 times negative 1/2 times x. So y squared equals negative 2x. That'll be our equation. So I find it much easier to just kind of graph things out to get a sense of what's going on, right? Instead of just looking at those points and trying to imagine it. Okay, let's go back here. All right, so we've been talking about parabolas with the vertex at the origin, but what if they're shifted, right? Just like before, so if the vertex is at hk, x minus h, y, oh, wait, that's supposed to be a k. Y minus k, x minus h, y minus k, x minus h, y minus k, x minus h. So this is supposed to be a k there. But you can see everything's going to be the same, just shifted, right? Our vertex is shifted, so we just go p units this way, p units that way to find the focus and directrix. So our equations get a little more complicated, but the idea is exactly the same. Okay, so let's do examples where we have vertex not at the origin. Example 4. Graph this equation. Let's see, there you can see it. Y minus 1 squared equals negative 16 x plus 3. So same thing, identify and label the vertex, axis of symmetry, focus, directrix, and endpoints. Okay, so let's see. First of all, where's the vertex? The vertex is going to be at negative 3, 1, right? The x value is negative 3 and the y value is 1. Okay, so there's the vertex. We know that, so we have y minus 1 squared equals negative 16 x plus 3. And we know this is the form. This here is our 4p. So we can see p is going to be negative 4. Okay, so let's graph this. And let's see if I can. So we know our vertex is at negative 3, 1. There's our vertex. And this is going to open which direction? The y squared is the y term that's squared, so it's going to open to the left or to the right. Okay. Our p is negative, so that tells us, so here's our vertex. Our focus is we're going to go 4 units to the left. 1, 2, 3, 4. Probably should label these. So this is negative 3, 1. This is negative 7, 1. Right? And our directrix, we're going to go 4 units the other direction. So 1, 2, 3, 4. Our directrix is going to be the point x equals 1. So the numbers aren't as nice and symmetric as before, but we're doing the same thing, right? We found our vertex. We're going 4 units this way and 4 units that way to find the focus and directrix. And now the endpoints of the lattice rectum, well, our p is negative 4, so it's going to be 8 units either direction. So 1, 2, 3, 4, 5, 6, 7, 8. What's that going to be? Negative 7, negative 7, right? 8 units that way. And this will be negative 1, let's see. 1, 2, 3, 4, 5, 6, 7, 8 will be about right here. So at negative 7, 9, right? Because we went 8 units up, 8 units down, since the endpoints of the lattice rectum are 2 times p units away from the focus point. All right, and now we can draw our parabola. There we go. Cool. All right, so sometimes they are not going to give us equations in a very nice form, and we're going to have to complete the square. By this point, we're getting really good at completing the square, are we not? All right, so let's think about how we can do this. X squared minus 8x minus 28y minus 208 equals 0. All right, we're going to want to move all the x's here and all the y's. Let's just think, what's the general form of our equation going to look like? X minus h squared equals 4py, right? Since we can tell our x squared is, or I guess it's going to be y minus k, right? Since x squared is our squared term. So this is going to be the general form of our equation. Okay. So let's move these terms over to the other side. 28y plus 208. And we're going to, we just have to complete one square, right? Only one of our terms is squared. So we're just going to complete the x term here. So negative 8 divided by 2 is negative 4. Squared is going to be 16. So we add 16 to both sides. Okay. All right. So we're working towards this. So this side, we can write this as a perfect square. X minus 4 squared. That looks good. Let's write this 28y plus 224. All right, we're going to need to factor out whatever coefficient we have for y, right? We just need this to be y minus k. So this part of the equation, we're going to have to factor out a 28. And if I was smart, I would have figured this out already, but I wasn't. So I'm going to grab my calculator and say 224 divided by 28 is 8. Okay. Yeah, this looks like it's in a good form here, right? What's our p? 28 equals 4p. So p is 7, right? 4 times 7 times y plus 8. Okay, so hopefully by now, this is starting to be pretty routine for you. You've been doing it for circles and ellipses and hyperbolas. Now we just have to do it for one term for parabolas. Okay, so now we've got this in a form where we can do all this stuff, right? Our vertex is going to be at 4, negative 8. Our p-value is 7. Whoops, not 4, 7. So for negative 8 is down here. There's our vertex. Ooh, so far down you can't see. 4, negative 8. Our p-value is 7. Our x-squared term, the squared term is x. So that means it's going to open either up or down, and our p is 7, so positive 7. So we'll go 7 units up. So there's our focus. So this parabola is going to open up, right? And then, look, I have enough room to keep it going. 7 units down is going to be at negative 15 for our directrix. Yeah? And the ends of our lattice rectum, so let me, this is 4, negative 1. The ends of our lattice rectum are going to be 14, 2p, 14 units either direction, so way over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 1, and then 14 units the other direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14. So those would be the 2 endpoints of our lattice rectum, and we can connect them like this. And there's your directrix. This would be y equals negative 15, right? And I guess we could label these. All right, so once we get this equation, same process, right? Sometimes you just have to do a little work to get there. All right, one last thing. Parabolas are there's a lot of applications of parabolas, actually. Because if this is parabolic, if this is a parabolic reflector, anything that comes in gets bounced to the focus point. Okay, so if this is sound, these are sound waves, or if these are light rays, they all get bounced to the same spot. Okay, so they have really important reflecting properties. So, like, they're used in telescopes, suspension bridges. To be honest, I'm not totally sure why they're using suspension bridges, but apparently they are. Microphones, radar equipment, mirrors, solar cookers, and heaters. Okay, so the parabolic reflectors are just super powerful because they focus all of the light coming in onto one point. All right, so here's one application question. A cross-section of a design for a travel-sized solar fire starter is shown here. Okay, so here's the igniter. The sun's rays come in and reflect off the parabolic mirror toward an object attached to the igniter. Okay, so all the rays come in and bounce to the igniter. So this is at the focus. Because the igniter is located at the focus, the reflected rays cause the object to burn in just seconds. Okay? So find the equation of the parabola that models the fire starter. Assume that the vertex of the parabolic mirror is the origin of the coordinate plane. Okay? So let's go back over here. All right, so this is the same diagram. So let's think. This is our vertex. So our vertex is at the origin. And we know that the focus is, this is 1.7, is at 0, 1.7. P is 1.7. So find the equation that models the fire starter. All right, well, it's opening up. So we know it's going to have the form x squared equals 4py. And we know our p-value. So x squared equals 4 times 1.7 times y. So let's see, 4 times 1.7 is what? 4 times 1.7 is 6.8. So x squared equals 6.8y. There's our equation for part A. And then they ask, find the depth of the fire starter. Okay, so we know that across this is 4.5. So this distance, so this like ends right here, right? And we know that this is 2.25, right? Because they tell us this whole distance is 4.5. So this distance is 2.25. So if x equals 2.25, what's the y value? So let's see, 2.25 times 2.25 is 5.062 divided by 6.8. We get that y equals 0.7444. Okay, so that depth is that y value. All right, so that's just an example of the kind of application problem you could do. And that concludes all of the conic sections that we're going to talk about. If you were going to continue on thinking about conic sections, we can start doing things like rotating them, right? Like an ellipse or a parabola or hyperbola, we can rotate the axis. We're not going to do that in this class, but just so you know, that's something that you can do, and in different math classes you will do if you continue on with math or engineering.